Hi there, this is Math 6, Unit 6, Lesson 12, Meaning of Exponents. So, we begin today with this first little picture here, which is what do you notice and what do you wonder kind of picture with some dots and lines. So as you take a look at that, what are some things that kind of pop out to you that you are wondering about or you notice here? Take a look at this, and I want you to share those out with your table mates, your partners, and your teacher, and see what it is that you notice and you wonder about this picture. Couple things that I notice here is it's definitely looks like a pattern, right? We see a pattern happening here, and on the outside, first thing I noticed was like it's a hexagon. It's like six sides here, and also looks like it has lots of lines of symmetry, right? Like I could draw a line there and kind of cut it in different points or fold it in half, and I have the same thing on both sides of it. I see the different colors. I have blue and yellow and green and red. And then I start here with a black one, which was interesting because it's the only one that's black. So when I looked at that, I thought, well, that's different. So when I looked at the black, I thought, well, what happens when you start at the black? And I see that the black then expands to three different red ones, right? We have 1, 2, and 3 red ones. So okay, so 3 lines come off of that black one right there. So then when I look at the red one, I notice that the same type of thing happens actually. 3 lines, 1, 2, 3, come off of the red one. And it happens here too. 1, 2, 3, and then 1, 2, 3. So from each little dot or different circle, 3 more branches kind of come off of it there, forming a new color for the new branch. If you look at the next one, look at this one here. We get 1, 2, 3. We go from the green to 3 yellows, and then from yellow it goes to 1, 2, 3 of the blues. Okay, so what's happening is we're seeing repeated growing groups of 3, right? It just keeps on repeatedly growing in a group of 3. Once you have 1, it goes to 3, and then the 3 grows to 3 more for each of those 3, and it continues there. Okay, and so in essence, it's like once you get to here, we're adding 3, and then we're gonna do it again. We're gonna do 3 and 3 and 3. So it's repeatedly growing groups of 3. Now, key thing there is that when you're doing groups of, when I use words like groups of, that's important because when we talk about groups of, we're also usually talking about multiplication as well, not just simply addition. Okay, so keep that in mind as we kind of move forward with today's lesson. All right, the genie's offer. You find a brass bottle that looks really old. When you rub some dirt off the bottle, a genie appears. Lucky you. Genie offers you a reward. You must choose. 1. You can get $50,000 right away, or a magical $1 coin. Here's what the coin does. It says the coin will turn into 2 coins on the first day. This is really key there, alright? So on day one, you actually have 2 coins. Okay? If it was just 1, it doesn't quite work. What we're going to do next. So keep that in mind. On day 1, it's 2 coins. The 2 coins will turn into 4 on the second day. Okay, so the first day it's 2. On the second day it's 4. The 4 coins will double to 8 coins on the third day. So the third day it's 8. And Genie explains the doubling will continue for 28 days. So just doubling for 28 days. That's pretty cool. So, the number of coins on the third day will be 2 times 2 times 2, right? And the third day it said you had 8, and so is that going to be what it is? Well, we know it's 8 on the third day because it's 2 on the first day, and then we double it for the second day, and then we double that for the third day. So an equivalent expression for 2 times 2 times 2 using exponents is 2 to the third power. Okay, and this is how we write exponents. It's 2, and it's being multiplied by itself 3 times. And that's what that number up in the top is telling us. That we're going to take this number, our base number here, this is our base, and our exponent is up here. We're going to take the base, and we're going to multiply the base however many times the exponent says. So in this case, it'd be 2 times 2 times 2. And so in our story here, our exponent represents the day for the magic coin. It's day 3, right? Day 1 is simply 2 to the first power. because it's the first day and we have 2 coins. On day 2, we have 2, which is what we started with, to the second power, which is 4. And now we're being told that day 3, 2 to the third power, of course, is 8. And so the information from the story is now right here. And we're writing it out in exponential form to show how that works. What do 2 to the 5th and 2 to the 6th represent in this situation? And then it says to evaluate those without a calculator. Okay, so 2 to the 5th is going to be, looking at our exponent, our amount on the 5th day. And then 2 to the 6th would be what we have on the 6th day, right? And so without a calculator, this means I have 2 times 2 times 2 times 2 times 2. I have 1, 2, 3, 4, 5 2's. And so 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. On the 6th day, 2 to the 6 is 2 times 2 times 2 times 2 times 2 times 2. But there's probably a quicker way of multiplying this out, right? Instead of going all the way across again, I could go all the way to here, which is the 5th one, and start at 32, because I know this all multiplies together to get to 32, and then 32 times 2 is 64. Okay? So, that's how that works there. How many days would it take for the magical coin to exceed, that means be more than, $50,000? That's a great question. Now to do this, you could keep doing 2 times 2 times 2 forever until you figure it out, but you could also use a calculator to help speed up the process a little bit there. Okay, so I'm going to show you on a calculator what I'm going to do, because we're just going to keep doubling it again and again. And there is a key on my calculator here, on this one, which has a little, I think it's called a caret there, where it fits into something. This button right here will allow me to use the exponent. Okay, so if I did the number 2 and then I type this number in, now I'm going to raise whatever number goes there. So let's do one we know. If I put a 6 right here, this is how you would write on a calculator: 2 to the 6th power, 2 exponent 6, and when I type equals, it's 64. Okay, so to find out which number would get me above $50,000, I could just try 2 to the 10th power, for example. And I can see the 10th power, I have 1,024. Now, the 11th is going to double that, and then it's going to keep doubling. So I'm not quite close. So let's try another number. Let's do 2 to the 15th power. Oh, that's getting closer. So I notice that 2 to the 15th is 32,768. That means 2 to the 16th is going to double this number, right? I could almost think about just like multiplying it by 2. Well, estimating 30 times 2 is 60. So this number is going to be greater than 50,000. Let's just look what it is. 2, use the caret, to the 16th power is 65,536. So, in our case here, how many days will it take to exceed, get over that amount? We would say, looking at this, it's going to take 16 days. Now, will the value of the magical coins exceed $1 million? So will it be greater than $1 million on day within 28 days? So what we can take a look at is we could say, well, let's go back here and do our 2. And let's raise that to the 28th power to see how much money would you have on day 28. So when we press equals, what do we get? Wow, look at that number. So 2 to the 28th power is 268435456. Let's come back in and add some commas. 1, 2, 3, comma, 1, 2, 3, comma. So if this was money, you don't have just $1 million, you have $268 million. That's a lot of money. So it'd probably be a good idea to take the genie's magic coin, because after 28 days, you're doing pretty well. Alright, so that's how that one works there. Okay. let's go ahead and look at one more activity, activity number 3. Says here are some expressions. All but one of them equals 16. So one of them does not equal 16. Find the one that is not and explain how you know. Okay. Well, here we have 2 to the third times 2. Well, this is really going to be 2 to the fourth because that can become a 1, and I could actually put them together. That's another lesson here. But this is 2 times 2 times 2 times another 2, which is really 2 to the fourth, like we said. And 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. So that's okay. 4 squared means 4 times 4, and 4 times 4 is 16. This one's interesting because you get 2 to the 5th power. Okay, so you have 2 times 2 times 2 times 2 times 2, all divided by 2. Now in terms of reducing, right, I can reduce this 2 and that 2, and I'm left with just 2 to the 4th, which we already said was 16. I could also multiply that out and end up with 32 over 2, which again reduces down to 16. Okay, so that happens as well. Another thing you'll notice later on when you get to be kind of in high school math, you'll play with some more exponents, and you'll just simply subtract. Instead of 2 to the 5th, you'll see this 2 to the 5th over 2 to the 1st, and you'll do 5 minus 1 equals 2 to the 4th. But that'll come up later. And right here, the last one, 8 squared. 8 squared is 8 times 8, and 8 times 8 is 64. So the one that doesn't match here is the 8 squared, because it's not going to be 16. There's no way, because we're not doing 8 times 2, we're doing 8 times 8. And then finally it says write 3 expressions containing exponents so that each expression equals 81. Alright, so to get to 81, first one I think of is 9 squared. Okay, so that works. That's 9 squared. That works, no problem there. I could think of then doing like almost like a, well, like one of these. I could do a 9 to the third over 9 to the first, right? Or just 9, because that's going to leave me really with 9 squared. To get to 81, I can also think about 3 times 3 times 3, which is 27, times 3, which is 24, or sorry, 24 is 81, and rewrite that as 3 to the 4th power. That will work okay. And knowing 3 to the 4th works, I could do 3 squared times 3 squared, because that's 3, 3, 3, 3. I could do 3 to the 3rd times just plain old 3. That works too. So there's lots of different things you can do. So in summary, when you write expressions like 2n, we call n the exponent. If n is a positive whole number, it tells how many of the 2 we should multiply to find the value of the expression. So 2 to the 5th tells us to do it 5 times. 1, 2, 3, 4, 5. We're going to multiply the number by itself. And then there are different ways to say 2 to the 5th. We could call it 2 raised to the power of 5, or 2 to the 5th power, or just 2 to the 5th. So there's different ways of describing what you see right there. So just keep that in mind a little bit as well. Okay? All right, we're going to pause there, let you work on your homework, and then we'll come back and check it together in just a second. Alright, homework time for Lesson 12, Unit 6, Meaning of Exponents. Select all expressions that are equivalent to 64. So what you have to do here is just basically work them out, okay? So let's see, we have 2 to the 6th power. This becomes 2 times 2 times 2, that's 3, 4, 5, and 6. So let's try this out. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and 32 times 2 is 64. So that definitely works. So 2 to the 6th is yes, then 2 to the 8th is a definite no. Alright, with a 4, we have 4 times 4 times 4. Well, 4 times 4 is 16, and then I do 16 times 4. I may not know what that is, so if I just do it real quickly here, 6 times 4 is 24, 4 times 1 is 4, plus 2 is 64. That works. 8 squared, yep, 8 times 8 is what? 64. So that works. 16 to the 4th power. There's no way that's going to work. Think about it. This is doubling that number and doubling that number. How in the world could that be the same? Not possible. And 32 squared, this is, remember, let's be careful, this is 32 times 32. This is not 32 times 2. That would work, but this is 32 times 32, so it would not work. Number 2. Select all the ones that are equal to 3 to the 4th power. We've looked at this one before. We did it with one of our activities. So 3 to the 4th is the same as 3 times 3 times 3 times 3. And now you might know that 3 times 3 is what? 9. And 3 times 3 is 9. And then 9 times 9 is 81. Does this look familiar to you? Does it look a little bit like what we did in our What Do You Notice and Wonder? A little chart like that? Yeah, kind of cool. So this is how that works there. 3 to the 4th is 81. So 7. No. Where did that even come from? 7? Oh, I know where it came from. That would be if you decide that I'm going to add 3 plus 4, which is not what you do there. So that's a no. 4 to the 3rd power. We just did 4 to the 3rd power up here, and 4 to the 3rd was what? 64. So that equals 64, and we want 81. So that's a no. 12. How would you get 12? Well, that would be a mistake if you did 3 times 4, right? So no. 81, definitely what we're looking for. 64, we've already said no to that one. And then 9 squared. Well, look what we have right here. 9 times 9 is what? 81. So that's correct as well. So number 2 is good. Number 3. 4 to the 5th is equal to 1,024. Evaluate the following expressions. Okay, so 4 to the 6th is going to be 1 more than that one. So it's like taking 1,024 and multiplying it by 4 more. Well, 1,024 times 1 more 4 is equal to 4,096. For 4 to the 4th, we can see that it's 1 less. So that means we're going to take 1,024 and we'll divide it by a 4, right? Because we are going to take a 4 away. And so 4 goes into 1,024 how many times? Goes in there 2 times. Goes into 22 5 times. And goes in 24 6 times. So we'd say 256. And the last one here, we have 4 to the 3rd times 4 squared. Well, what is that altogether? We can combine those because they're the same bases, and so this really becomes 4 to the 5th power. Let's just verify that. Here's 4 to the 3rd times 4 squared. How many 4s do we have altogether? 1, 2, 3, 4, 5. So it's 4 to the 5th, which is what we started with, and it is going to be 1,024. So it's the same thing. So our answer is 4,096, 256, and 1,024. Using exponents, write 3 more expressions whose value is 216. So a variety of things you can come up with. A couple you could do, right? The easier ones. You could think about 6/3 being the same as 6 squared times another 6. That works just fine. Another one would be the division way, where you make this 1 more. So 6 to the 4th power, and we divide by 1/6 there. Are there other ways of doing it? Yeah, there are other ways, and so one of the things that my book was suggesting was, instead of using 6s, try to find some other numbers you could use. Okay, so you could do that. You could recognize that 6 is actually made up of 2 and a 3. So let's take this one here. Let's do 6 squared. Let's break this apart. So 6 squared times 6. I could also write that as 6 squared times 3 times 2. Right? Does that work okay? So that's another expression. I could break the 6 squared up into 6 times 6, and then times 3 times 2. Oops, sorry. And then I could break the 6 up into 3 times 2, this up into 3 times 2, and I already have a 3 times 2 there. So if I just keep breaking it apart, I end up with 1, 2, 3 3s, 3 to the 3rd, times 1, 2, 3 2s, so 2 to the 3rd power. So this is another one the book suggests, and how you'd get there would be to kind of decompose that 6 and take it apart to see what multiples go into or form that 6 until you get down to there. All right, number 6 is some review from previous ones, just working with some decimal things here. So again, to solve this one, what do we want to do? We want to add 2.01 to both sides. I'll zoom in here a little bit for you since it's kind of small. And we're going to have a 1 there, a 5 there, a decimal there, and a 7 there. Over here we're going to subtract 2.01, subtract 2.01. So 0 minus 1, I can't do that. So I will borrow 10 minus 1 is 9, 4 minus 0 is 4, decimal there, and 5 minus 2 is 3. Over here we're going to divide by 10, divide by 10. And so when I divide by 10, what does that mean I'm going to do? It just simply means I'm going to move the decimal place here 1 over. So I keep the same digits, 1371, but instead of having the decimal here, when I divide by 10, I'm moving the decimal 1 place to the left, and there I am, 1.371. And this one, when I divide by 100, I'll take the same digits, and I'm going to move the decimal place over 2 places. Right? And there you go. And number 7. Which expression represents the total area of the large rectangle? Well, let's look at the next page for my large rectangle. So I can turn my page. The large rectangle is here. And we see the large rectangle is going to be 6 times the combination of 5 and n. 5, m and n. That's where I got 5 from. It's early in the morning. So we're looking for something that says 6 times m plus n, right? Something along those lines. Now this square here is 6m, and this one is 6 times n, so 6n. So we can also have the combination of 6m plus 6n. We can add those things together there. These are all possible things, and we can see how this came from distributing 6 times m, 6 times n. Let's zoom out here and look back at what our choices are. And we have 6 times m plus n, which matches that one. Great. 6n plus just m by itself. Well, you can't keep the m by itself. The m has to be joined with the 6 to be able to work out. So that's a no. 6 times n plus 6 times m. We have that there. That's correct. The order is not super significant, so it's okay. 6 times m times n. Nope, these have to be added first, so that's a no. And this one just simply reverses the order around and does n plus m times 6, so that's correct as well. Number 8, is each statement true or false? And explain your reasoning. Okay. Alright, so what's our reasoning for this first one? Here we have 45 over 100 times 72 equals 45 over 72 times 100. Well, let's rewrite it like this. This can be 45 over 100 times 72 equals 45 over 72 times 100. So, are those equal? Meaning, can you move things around a little bit? Well, not really, because look at it this way. In this case here, I have 45 over 100, and here I have 45 over 72. I can't just move numbers around and make this look the same in any way. Sometimes, because of the way multiplication works, I can reverse those two, and I can have 72 over 100 equals 45, times 45 equals 45 over 72 times 100. That's not going to work, doesn't look the same. So I just can't make that work out. It's just not going to be equal to each other. So this is going to be a false statement. How about this one? This one's interesting to look at because of what didn't happen here. 16% of 250 means 16 out of 100 times 250 is equal to 250%. Well, that's 250 out of 100 times 16. Now because it's multiplication, I can move these things around a little bit. I can rewrite this as, I think of this as 6 times 1 over 100 times 250, if I break apart that one. Now if I shuffle stuff around, I could put the 250 on top of the 100 and write 250 over 100 times the 16. Well, does that equal what we started with on the right side? It sure does. So this one is definitely a true statement. It doesn't seem true by reading it, but when you look at the numbers that you're playing with and how you can manipulate the numbers, it is true. Okay, that's it for today. Have a great day, and we'll see you next time.